All right, so we've talked about implicit differentiation in previous levels of calculus, and so now we might want to talk about implicit differentiation in multivariable calc, for example, right? And so the main driver of implicit differentiation in multivariable calc is going to be what we like to call the implicit function theorem, right? Implicit function theorem. Now, what does it say? What does our implicit function theorem say? Well, it says that, and this is going to be proved in advanced calculus, but and I'm going to read it word for word right now, okay? So it says, quote, that under, it states that if we have a function f defined on a disk containing a comma b, point ab, where f of ab is equal to 0 and the partial of f with respect to y at ab does not equal 0, and the partial of f with respect to x and y are continuous on the disk, then the equation, the function of f defined by x and y, is equal to 0, defines y as a function of x near the point a comma b, and the derivative of this function is given by the equation as follows, where we have del y, del x being equal to negative f sub x, f sub y. I'm using sub notation here to basically say partial. So the partial of f with respect to x over the partial of f with respect to y, a negative value of that, obviously. And so what that means as practice is that we can do implicit differentiation of any given function so long as we set it equal to 0, right? We solve it for 0, and then we find the partial of f with respect to x, and then we can do the same for y. And now this kind of theorem is going to be proved later on, and this is kind of more an advanced topic that's not really discussed in calculus at all, in Calc 3 at all. And so it's going to be discussed later, but we can use this certainly using implicit differentiation. And actually, we can do this for any number of functions and with any number of variables. So we might have, for example, a multivariable function z, or we might have a z, for example, being defined by f of x comma y, and so del z del x is going to be equal to negative f sub x over f sub z, and the same goes for y. Del z del y is going to be equal to the partial of f with respect to y over the partial of f with respect to z. And so what does that mean here, right? We take the bottom of whatever is happening over here, that x, for example, and we bring it up to the top, and we're finding the partial of f with respect to x over that top over here, which is y over here, and we're finding the partial of f with respect to y. Same goes over here, right? We basically switch the variables that we have, so we're finding the partial of f with respect to x first, and the partial f with respect to z in the denominator second, and we have to negate it, right? We have to negate our value, and this is going to be more clear when we take a look at a couple of examples. But this is essentially our implicit function theorem. So let's take a look at our first example. All right, so we're being asked to find dy dx, given that e to the power y sine x is equal to x plus x y. All right, so find dy dx. This should be pretty simple once we actually get started. So we are going to start off by saying that we're going to create a function, basically, x comma y. That's going to be equal to, and we're going to set this we're going to set this equation here equal to 0. And so what we're going to do is we're going to say e to the power of y sine x minus x minus xy is essentially going to equal to 0, right? So if we set the equation equal to 0, and that's going to be basically our function. right? That second expression, that larger expression is going to be our function, right? And so the derivative of y with respect to x is simply going to be negative of f, the partial of f with respect to x and y. And so what is the partial of f with respect to x? Well, that's going to be, first, in order to address this first term over here, e to the power of y is going to be constant. So we're going to have cosine x, we're going to have e to the power of y cosine x minus y, or sorry, minus 1 minus y. And that is essentially going to be our partial derivative over there. Our partial with respect to y, well, that ey sine x is going to stay the same, right? Ey sine x is going to stay the same. And then we're going to have negative x, that's going to be 0 because that's a constant. And then we're going to have negative x in the denominator. And so that is going to be our answer, basically, right? Our answer is going to be negative e to the power of y cosine x minus 1 minus y over e to the power of y sine x minus x. And that is basically our basic idea, right? And so that is our answer. Let's take a look at another example. All right, a little bit more complicated. We're asked to find del z del x and del z del y given the following equation where we have yz plus x ln y is equal to z squared. All right. Again, we're going to create our function first. Our function first, defined by x, y, and z. That's going to be equal to yz plus x ln y minus z squared, which is equal to 0. And so that's going to be our function. Now to find del z del x first. And that's going to be equal to first negative f sub x over f sub z. That's going to be negative f sub x. Well, the partial of f with respect to x, that yz term becomes 0 because it is constant. That ln y is a coefficient to x, and so that's going to be ln y over there. And that negative z squared is going to be 0, right? So we have negative ln y up top. The partial of f with respect to z is going to be, well, that yz becomes y, right, because that the y is a constant. X ln y, we take that out, that's 0. And then we have negative 2z over here. In fact, we can rewrite this as follows. We can write this as ln y over 2z minus y, distributing the negative into the denominator. Okay, now we can do that for del z del y. That's going to be negative f sub z, or sorry, f sub y over f sub z. And so what is the partial of f with respect to y? Well, we have basically z in that first term over here. In that second term, it's going to be a little bit more complicated. We're going to have the partial with respect to y is going to be x over y, because the ln y turns into the derivative of ln y is 1 over y. And that negative z squared, that's constant, so that we take that out. Okay, and so now we want to find the partial of f with respect to z. That's going to be y plus x ln y, which is constant, so that's going to be 0. That's going to be 0 basically. And we have, again, negative 2 0. Okay. So we can first multiply a y on top of the z. So we can do multiply y in the numerator and y in the denominator. So we're going to have yz over y plus xy. That's going to be all over 2z minus y. Cleaning it up a little bit more, we're going to be left with x plus yz over 2yz minus y squared. And that is going to be our partial of z with respect to y. Okay, so it's a pretty simple concept actually. Very short video. Thanks so much for watching. If you have any questions, please feel to leave them in the comments. Otherwise, once again, thank you so much for watching, and yeah.